Hello, today I'll be talking about multi-arm bandits for my CS221 project. First, I'll introduce the problem setting, then I'll talk more about why we care about bandits, and finally I'll talk about some specific algorithms I implemented and showcase some simulation results. So first, what are bandits? The name might sound quite funny, but really it's just a set of problems related to sequential decision making under uncertainty. The name itself comes from a generalization of a nickname for a slot machine, which is a one-armed bandit. You pull a lever and you win or lose some money. For multi-armed bandits, there are multiple arms or actions you can choose from, and pulling one will give you some sort of reward. So before I jump into a more detailed setup for bandits, I wanted to explain it in a way that might make more sense for people with a CS221 background. In this course, we learned a little bit about reinforcement learning, where we have this loop of an agent interacting with the environment by taking actions every round, and then those actions would influence their reward and also importantly influence future states. So then an episode of reinforcement learning might look like state, action, reward, state, action, reward, state, action, reward, and so on. It makes sense to view the general bandit problem as RL without state, or you're given a state that's independent of the actions you took. This is what that would look like. An episode might then look like action, reward, and so on. The rewards are random and sampled from a probability distribution that's unknown to the agent, and each arm typically corresponds to a different distribution. If you're familiar with the Bayesian framework, we might know the overall family that the distributions belong to. After that, the agent has the same freedom as a typical RL agent, where we can choose which arm we want to pull to maximize reward in the long run. So why do we even care about bandits? At its core, the simplified setup of bandits really allows us to focus in on a core theme of reinforcement learning, which is the exploration-exploitation problem. Since we don't know anything about the arms beforehand, we want to explore enough so that we can identify an arm with high reward, while still pulling arms with high reward often enough so that we can get high reward on average. I also snuck in a little bit about information here. Well, usually the only way to get information about an arm is to choose that specific arm. There are certain bandit settings where you can get more information about other arms after pulling that arm. For example, there might be one arm that we're really confident has low reward, but we also know that it might reveal useful information about the optimal arm. So in this case, we still have some incentive to pull that arm. Finally, I want to touch upon the idea of regret. We all regret decisions we make in life, and our agent is no different. This is kind of like saying, oh, how much reward did I miss out on by not picking the best arm every time? In this sense, you can kind of see how the typical RL objective of maximizing reward is equivalent to minimizing cumulative regret. Now I want to talk about some algorithms the agent can use. Of course, a really simple one is the random algorithm, which, as we'll see, performs horribly. There's also the greedy and epsilon greedy algorithms, which exploits by choosing the best arm identified so far, but also explores by choosing a random action once in a while. These algorithms typically don't perform as good as others that explicitly incorporate some notion of uncertainty. So for example, upper confidence bound algorithms try to estimate confidence bounds on the estimated means of arms, and then try to choose an arm optimistically. In this case, either we end up getting high reward, or we learn something and reduce our uncertainty a little bit. Thompson sampling is a form of probability matching, where it maintains a posterior distribution and that chooses an action with the probability that it's optimal. And information directed sampling is a technique where we explicitly compute sort of information ratio, which is a ratio that balances expected regret from pulling an arm with the information we would gain from pulling that arm. So now let's look at what kind of rewards we can get. One example is the Bernoulli setting, where we receive a reward of either 0 or 1 with some probability, or we can have the rewards distributed to something like a Gaussian or Poisson. Finally, we can have slightly more structure. In linear bandits, there is an unknown theta vector, and all the actions have their own fixed known feature vectors. The rewards are then given out based on this dot product plus some Gaussian noise. So, as a summary for what exactly I did in this project, I implemented my own Bandit simulator from scratch. I implemented all of the algorithms I mentioned before. I read a lot of the papers for the algorithms and tried to understand their theoretical results. Tried to work out some of the proofs on my own with varying success. And finally, I ran a bunch of simulations. Here are some of the results from those simulations. These are plots of cumulative regret over time, averaged over 2,000 independent trials each. You can see in the really messy graph on the left that the random algorithm is really no good at all, whereas epsilon and greedy tends to perform better, and a lot of the more advanced algorithms perform even better than that. This might be easier to see in the middle graph where I've pulled out epsilon greedy and compared it against the three advanced algorithms. Finally, the plot on the very right is a cumulative regret plot, but with both axes in log scale. It becomes a little easier to see how the regret scales with time in this way. The dotted line has slope of 1/2, and it's a function that scales with square root of time. You can see that epsilon greedy scales worse than that, while other algorithms here seem to scale better. Okay, so I am out of time, but I will include a little live demo. Um, the code itself is in an absolutely horrible state, so I won't show you that. But I will show you that it runs pretty fast, since I made it run lots of simulations in parallel. Okay, that's all from me. Thanks for watching.